Hello, I'm Dr. Peter Carter of British Columbia in Canada. I'm making this video on climate change and food security to help people understand that we're in a dire food emergency with respect to already committed global warming and climate change. And I'm doing it for this website of mine, climatechangefoodsecurity.org. On the home page, I want to point out that although the video is about what the climate models tell us about food scarcity, food losses, the most sensitive indicator of food insecurity and food losses around the world, of course, is the food prices. I'm not going to be talking about food prices anymore after this, but just to introduce this theme, that's the first thing we need to be concerned about. And here is the current FAO, Food and Agriculture Organization of the UN Food Price Index. And it looks like our cheap food prices could be very much a thing of the past. This is 1990 here. Here's 2007. They jumped up in 2007, came down again, and then jumped up even higher in 2012. This is a quote on the Climate Change Food Security website. It's from the American Society of Agronomy and the Crop Science Society of America and the Soil Science Society of America of 2011. So that's a combined position statement, which says that unless the emissions of greenhouse gases are curbed significantly, their concentrations will continue to rise, leading to changes in temperature, precipitation, and other climate variables that will undoubtedly affect agriculture around the world. That's the fact of it. This video is going to prove it. Our topic is food security. It's completely incredible how there is little to no awareness at all on the emergency situation that we're in today, on our food security at already committed global warming and climate change. We're going to have a look at a couple of graphs on food productivity and climate change published in 2010 in this excellent publication by the National Research Council in the United States called Climate Stabilization Targets. And this is actually a pretty thorough assessment of global climate change in general. These two graphs are the climate crop model presentations in the food section of NRC's Climate Stabilization Targets. These two graphs really are the most important graphs in the world, although very few people are aware of them, because this will tell us whether we're going to get food to eat or not. And what it tells us, these graphs are also proof positive that continuing to pollute the atmosphere with greenhouse gases and continuing to build more sources of that pollution is without question the worst ever crime ever against humanity. And actually it's a fact against all humanity, because it's against all future generations, as well as billions of people alive today. We're going to be looking at these climate crop model results, these graphs of various crops in various regions. But before we do, there's a very important context we have to set in our minds, and that is today's global warming and climate change commitment. Today, the global average temperature increase from pre-industrial, which you see here, is 0.8 degrees C, but we are today committed to a much higher temperature increase than that we cannot possibly avoid. The first commitment that is impossible to avoid is the climate system science, and that's the climate system inertia, and that means we're committed to double today's temperature increase. So we are today in reality at 1.6 degrees C, and that's just purely from the climate system inertia. That's forgetting about all the inertia of having to make the changes which we have to make to avoid global climate catastrophe, which of course is going to take time. That's very well explained in the NRC's climate stabilization targets, which we're looking at. The other temperature increase, global warming, climate change commitment that we really need to be aware of is the policy commitment, and that's huge. The combined national policy pledges filed by governments with the United Nations under the climate change negotiations add up to a catastrophic global temperature increase of 4.5 degrees C by 2100. So We absolutely have to do something about that one because that's right off the scale. The scientists never imagined that we would be insane enough to be looking at above 4 degrees C. The scientists are now saying that it looks like we're committing ourselves to 4 degrees C, and indeed we have done. Because of these national policy pledges, they commit us to a temperature increase of 4.5 degrees C. You can check this commitment out at Climate Interactive's website on their climate scoreboard. That's where it's calculated using the climate models, the 4.5 degree C commitment. This top graph is the NRC's own representation of the climate crop model results, and it's by nations and the top world cereal grains. So we have United States maize, United States soybean, Asia rice, India wheat, and Africa maize. Here are the changes in the yields. This 0 is the baseline. This is your 2000 crop productivity. And down here then is declining yields. On the bottom we have global temperature change, the global temperature increase from pre-industrial. And this also takes in a couple of adverse effects of the climate change as surrogates to the temperature. This graph here is the NRC's presentation of the Ipcc's crop model results published in the 2007 Ipcc assessment. When you go to the IPC assessment to find the crop model results, you have to go to the long technical report, and there you'll find lots of different graphs, and it's all a bit overwhelming and confusing. So NRC has done us a great service to compile all these together and present them in the one graphic, like their own presentation. This is again crop yields. There's the 0, there's the baseline of crop productivity around now, year 2000. And the geographical regions that the IPCC presents are according to latitudes. So we have mid-high latitudes, and in the northern temperate regions, that's where all the best world food productivity is situated. And the IPCC also presents low latitudes. And so that's the tropics and the subtropical regions. The IPCC presents the crop model results against a temperature increase from year 2000. So we have to convert that to the normal standard of from pre-industrial, and IPCC tells us to do that we have to add 0.5 degrees C. And so this bottom temperature grid here is from pre-industrial. And so it correlates with the NRC's graph up at the top here. What is at the same time the most obvious lesson from these climate crop models, and also very much the most important lesson, and that is simply that all crops in all regions under global warming and climate change go into declining yields. And the higher the temperature is, the more the yields decline, the faster we are losing our food. We're now going to get down to discovering the grim news about what these climate change crop models should be telling us. You'll see I've got two vertical lines here marking two global average temperature increases from pre-industrial. This one here is a 1.5 degrees C global temperature increase there on the IPCC graphic. And this one here is 2.7 global temperature increase from pre-industrial. Above a global temperature increase of 1.5, all crops in all regions have been tipped by the effect of the global warming and climate change into declining yields. So all of these, even the least relatively vulnerable crops and regions, are declining above a 1.5 degrees C increase. You'll see that some of these crops are assumed to start off with a moderate degree of global warming and effect of carbon dioxide on a brief but moderate increase, as the IPCC puts it. But at 1.5 degrees C, the crops are declining. Now this is really important. It's not pointed out particularly by the climate change scientists, but it's very important clearly because this is the point. This is the temperature and the climate change at which the global warming and climate change are harming the crops. And from there on, inevitably, the yields will continue to decrease more and more and more. So this is the danger limit which we absolutely must be avoiding. The scientists tend to give the effect of declining yields more in terms of a decline below the baseline, but this is clearly not good enough for presenting disastrous to catastrophic losses of food productivity from global warming and climate change. And this 2.7 degrees C is where all the crops in all regions have declined. They have been declining, most of them, for some considerable period of time, and even the least vulnerable ones now have declined below this zero baseline in both presentations of the climate crop models. So that's 1.5 degrees C when all the crops are tipped into decline, showing damage from global warming and climate change, and the much less important 2.7 degrees C, where all crops in all regions have declined below the baseline, and it's way, way too late to save the world from food catastrophe at this point. We'll now look at a little bit more detail at what happens at 1.5 degrees C temperature increase. And relatively speaking, that's not that high because we're at 0.8 degrees C today, with the various cereal crops according to the various nations, and the results are quite shocking. Here's the marker that I'm going to use for the 1.5 degree C increase, and the first two crops that we come to, and they have a 20% decrease at this 1.5 degree C temperature increase. The first two crops we come to are Africa maize. So maize in Africa at 1.5 degrees C, 20% loss. We're absolutely committed to 1.5 degrees C as we stand today because of the inertia of the climate system, the ocean heat lag. But what's this other one, this red one here? Well, this is United States maize. African maize and United States maize, they do just as badly. And this is because in both cases, the vast majority of the maize is rain-fed. And this is pointed out in some detail by the NRC in this report that we're basing our examination of food security on. So at 1.5 degrees C, disastrous reductions for maize in both the United States and Africa. Next one we come to is this purple one, and that's India wheat. So India wheat is about 17% loss, so that's disastrous as well. And then when we go up to the relatively less vulnerable ones, we get to United States soybean, which is the blue one here, and Asia rice, which is the green one. And now you can see quite clearly that at 1.5 degrees C, even the less theoretically vulnerable crops are into a decline. This is most important. The scientists don't point this out particularly, but what we need to do is, of course, is to find when is the temperature increase at which the global warming and climate change is actually doing damage to the crops. And of course, the way to find that is when they start to decline. The reason for that's rather obvious, because we can't put things in reverse. Global warming is not going to go away. Global warming is guaranteed to increase. That's why we have to try and use these climate crop models in the most sensitive manner in which we can. Climate crop models are very insensitive to global warming and climate change, and that's because they lack a very large number of the most adverse impacts. The models are still in development. The models are still work in progress. So really, it's highly questionable whether we should be relying on these models at all for assessing our food security under global climate change. If we take a look at them individually, Asia rice, this is the one that is tipped into decline at 1.5 degrees C. The blue one here, United States soybean, that's tipped into decline at 1 degree C. The other one, they're declining at under a 1 degree C temperature increase. And at 1 degree C, Indian wheat goes into a much steeper decline. United States maize and Asia maize, as we've already looked at, it takes a relatively small temperature increase to put those crops into decline. So at 1 degree C, they're into decline. Here's the Ipcc. The climate crop model results in mid to high latitude and to low latitude. And we can just pretty quickly go through the same procedure. Here we are at 1.5 degrees C, global average temperature increase from pre-industrial, and there's a low latitude maize going into decline, and there's low latitude wheat going into decline, low latitude rice going into decline, and there is mid to high latitude wheat going into decline. So all the crops in all the regions are going into decline from just a 1.5 degrees C increase from the pre-industrial. I'll just go over the decline below the baseline below today's productivity, today's yield, because this is what the scientists are generally referring to. but it really isn't, unfortunately, that important, because it's going to be way too late to do anything about it by that time. So by 1 degree C from global temperature increase from pre-industrial, the bottom three are in an established decline. That's United States maize, India wheat, and Africa maize. So we move along further up here. The next one goes into decline below the baseline is United States soybean, and that's just a little bit above 2 degrees C. And then when we get to this 2.6 degrees C, least vulnerable region on this climate crop model is Asia rice, and so that's going into decline below the baseline at 2.6, 2.7 degrees C. Now we'll take a quick look at the Ipcc climate crop model ensemble, published in the last assessment in 2007. The geographical regions, the crops are similar. The geographical regions mid to high latitude and low latitude. And this grid here is the global temperature change from pre-industrial. By 1 degree C, we see that low latitude maize is in an established decline below the baseline. And we move further along, we get to low latitude wheat at 1.5 degrees C. And after that, the low latitude wheat has declined below today's baseline productivity. A little bit further on, we get to low latitude rice, declined below today's productivity at about 1.7 degrees C or so. And maybe just a little bit further along from that, we get to mid to high latitude maize, and at about 1.9, or we could say 2 degrees C, that low latitude maize is gone into a decline below today's baseline. The least vulnerable one, according to the climate crop models, is the mid to high latitude wheat, and that's because of the assumed carbon dioxide fertilization benefit, which you'll see only lasts till about 1.5 degrees C. And then if we go to 2.7 degrees C, even the low latitude wheat with the assumed CO2 fertilization benefit is declining now below today's baseline. We haven't quite finished with the Ipcc's climate crop model results, because although it's difficult to find amongst all the different graphs and different symbols and numbers in the technical report, there are two examples of something which is most important, which is addressed by the National Research Council in their 2010 publication, and that's rain-fed crops. The vast majority of the world's food is produced by rain-fed crops. So first of all, we're going to look at the Ipcc's result from rain-fed wheat at mid to high latitudes. We've just looked at wheat at mid to high latitudes as apparently the least vulnerable of the crops and regions. But if we overlay this Ipcc wheat graph, which includes the rain-fed here, it's a very different story. So this is rain-fed wheat in the drier agricultural regions. And if we look at the 2 degrees C here, for example, where the wheat is just coming down from its assumed carbon dioxide fertilization benefit, in the rain-fed situation, it's completely different. It's 10% below the baseline already. And when we get above 2.5 degrees C increase from pre-industrial, it's over a 20%, it's a 25% loss from the baseline. So that is huge. And that situation is just as disastrous as the other crops and regions that we've looked at. The other rain-fed situation that the Ipcc gives us is rain-fed maize at low latitudes, and that's a staple for a vast number of people. This did very badly in the Ipcc general result of maize that we were looking at, but if we again overlay rain-fed maize in low latitude, and again it fares pretty well twice as badly as apparently the general graph does, similarly to the wheat, which fares twice as badly. Because if we look at 1.5 degrees C here, we see it's at a 15% yield loss from the baseline at just 1.5 degrees C above pre-industrial, and then it goes into a very, very steep decline. And I should have pointed that out with the rain-fed wheat as well, up to when you're getting up to between 1.5 and 2 degrees C and beyond, there's a very steep decline in these rain-fed crops. You know, there is one other final thing that I have to show. That is a very important aspect of the climate crop model results, which is not demonstrated in the Ipcc assessment, but is shown in the NRC's climate stabilization targets in their food section of their 2010 assessment. And to show this, I've taken the bottom three, the worst three yields, because that demonstrates it best. So the bottom three, the worst performing regions and crops, are first Africa maize, and the next, even worse, is United States maize. And yes, when we get to above 2 degrees C, in fact, American maize fares worse than even African maize. I certainly want to reinforce that point. And then the very worst is Indian wheat, which is the purple. What I want to point out is that we've been looking at these lines here, of course, but these are the mean of a very wide range of the climate crop model result. There is a big risk that they may be even worse than this. And in actual fact, because the climate crop model results fail to capture so many adverse impacts, we can be confident that they are going to be worse than this. And so we really need to finish up this video by looking at how far down the climate crop model yields tell us that the losses could be. What these two shadings here, they show us the United States maize, which the mean is here, but the climate crop model lowest result is right down here. And if we're looking at the very worst one, Indian wheat, there's the purple shading, which is the lower range, the worst result from the climate crop models of India wheat. And it does indeed make an absolutely huge difference. If we go here to 3 degrees C and move along, we see that there's about a 45% loss in Indian wheat at a 3 degrees C global average temperature increase. But the models tell us that that loss could be as great as a 70% yield loss at 3 degrees C. If we're looking at a risk assessment and a catastrophic risk aversion policy, we would surely pay attention and go by, in fact, the outside the worst aspect of the range of the model results, and not simply rely on the mean. The final statement of this, and is where I started off by pointing out that the climate crop model results failed to capture a large number of the biggest adverse effects. And so we've got to expect that, as the NRC states, that at the end of the day, in the real world, the yield losses are going to be considerably worse than the crop model results indicate to us. And we can cover ourselves by that to some extent by taking for risk the lower aspect of the wide range that the climate crop models give us. And you'll see the higher the temperature, the larger the difference. So if we're at a 1 degree C global temperature increase here, there's not a big difference between the mean and the lower range yield and the greatest yield loss. But when we get up to 3 degrees, there's a huge difference between the mean and the risk of probability, as the scientists call it, of a far greater yield loss. So lots to think about, lots to pay attention to, lots to learn, and lots to get engaged in protecting our food security from global warming and climate change. It's looking extremely bad.